Okay, this is examples 9.1 on the fundamental idea of a logarithm and graphing logarithms. And at first, I just want to get you this basic idea of what a logarithm is. We have just finished our exponential chapter, and so we are very familiar with this form of our exponential equation, where we have our variable in the exponent. But now we're going to look at the inverse of exponential equations. So you know that those are ones that are reflected across those lines, y equals x. And of course, if we were going to take a look at our exponential equation, which, our base is greater than 1 if we have growth. Remember that it looked like this. That was our bases that were between 0 and 1. We had decay. But we're not going to be taking a look at those when we're just getting our parent function going. And so if we were going to take a look at this exponential function and see what its inverse looks like. Okay, so our inverse is going to be reflected across this line y equals x. And when we reflect it across this line equals y equals x, we get something that looks like this. And so this is our reflection, our inverse of an exponential function. So exponentials and logs are tied together. In other words, we switched the x and the y values, and so we get this x equals b to the y power. And then what we do with a logarithm, which a logarithm is our inverse of our exponential function. So there's several things I want you to talk about that I want to have you have in this definition here. Our logarithms are the inverses of exponential functions. Also, I want you to notice and note that it's just a new way of writing an exponential function to get the exponent by itself. And finally, the reason that we are getting the exponent by itself, the reason that logs help us is to solve for unknown exponents. Okay, so for instance, let's say we knew that swine flu was growing at a rate of a natural rate of y equals e to the x. Well, and so say this is the rate at which it's growing per day. I don't know. And I'm just totally making that rate up. But if our question was, when will 80,000 people have the swine flu? Then you would be able to plug in 80,000 here. We would be able to, throughout this chapter, learn how to solve this. And real quickly, what we would be doing is we would take the natural log of both sides. And so then that would give us x. And so then we could just take the natural log of 80,000. And we would know that that then is the time that, and if we were talking, let's say we were saying days, that the rate of that is that in days. But if we were going to do that, then we would say that if it grew at that rate, maybe that's months, but then in 11.28 months, whatever rate it was that we said, that's when 80,000 people will be infected with swine flu if it continues at that same rate. So um, anyway, so that's where we're headed. That's how logs help us. Logs help us because we can then solve for unknown variables. We can solve for that time that is unknown. All right, so let's go ahead and kind of link these things together, make a connection between x equals b to the y, which is the inverse of an exponential, and when it's written in its logarithmic form. The exponent, of course, you can see is right here, the y. But look over here. When it's in its logarithmic form, the y is by itself. See, that exponent got isolated. Over here in our exponential form, the base is still our b here. Look where the base is located when we have written it with a log. And over here, our answer was there. And here, notice where our answer is within the problem. So that may seem a little bit abstract because it's done without numbers. So let's take a look at exponential and logarithmic form with numbers. So here I would say 4 to the third power equals 64, but notice how it's written in exponential form. 4 to the third power equals 64. And on the second one, 2 to the fifth power equals 32. But over here, 2 to the fifth power equals 32. Well, right now you have all of those numbers there, but in the future, if this was an unknown, 2 to what power equals 32, or maybe it's even a number that isn't a regular number, we're eventually going to learn how to solve that. Okay, so let's write these logarithmic equations in exponential form. So here we would say 9 to the 1/2 equals 3. So that's exponential form. 9 to the 1/2 equals 3. And you know that to the 1/2 is the same thing as the square root. And so just to kind of solve that and check that for you, there it is. This one is saying 4 to the negative 1 power is 1/4. 4 to the negative 1 power is 1/4. And you remember that when we have a negative exponent, it's going to make that base reciprocate, or you will have a reciprocal of that base. And so that's why we have 1/4. Okay. Next, we're going to take an exponential equation and write it in logarithmic form. So I'm going to be saying log with a base of 9 to the 3/2 power. So I put that 3/2 over there on the right-hand side is 27. So we're getting straight where we're putting everything. 9 to the 3/2 power is 27. And let me explain this to you. We have not spent extensive time on exponents, but I want to remind you from Algebra 1 that the power is in the sky and the root is in the ground. So if we have 9 to the 3/2, the 3 is our power and the root is our square root. And so I would make it smaller first. So I would take the root first, and the square root of 9 is 3, and then raise it to the power, and that's how you get 27. So let me say that again. 9 to the 3/2, 3 is your power, and 2 is your root, which is, of course, a square root. I didn't have to have this 2 written right here. But I would take the root first because I'd get it smaller before I cube it. And the 9 to the square root is 3. And 3 cubed is how I get 27. Okay, so let's go through working this one. If I wrote this in logarithmic form, I would be saying log base 4 to the negative 1/2 power is 1/2. So there's my answer. But let me just go ahead and practice that with you since we haven't spent extensive time doing those. 4 to the negative 1/2. Well, what's that saying? Well, get rid of this negative, make it a positive exponent by reciprocating this base. So I would say 1/4 to the positive 1/2. That's how I would take care of that. And then what's this to the 1/2 power? Well, that's square root. So that's going to say the square root of 1/4, which is, of course, 1/2. And that's how you end up with this 1/2 that they tell you that it's equaling. Okay, so I want you to evaluate these next ones without a calculator using your understanding of a log. And so since this equation would be log base 5 of 25 equals y, then I would be saying 5 to what power equals 25? Well, you can see that 5 squared is 25. So that exponent that I solved for is 2. Here, I would be saying 1/6 to what power is 36? Well, if you do not want to have that as a fraction, you want to make them together, I'd probably say 6 to the negative y equals 36. Some people can just see the answer from the beginning. Those who cannot, change this into a whole number. And then, of course, 6 to the negative y equals 6 squared. So then I'm going to set those equal, and y is negative 2. Next, this one is saying 4 to what power is 4 to the 5/6? Well, you can make the exponents equal, so y is 5/6. 27 to what power is 3? Well, it's getting smaller, so I'm going to take the cubic root of it, and I know the cubic root is 1/3. So I can just straight away say I know that y is 1/3. But if you want to see the technical way how you could solve this, I could get like bases. 27 is 3 cubed to the y power equaling 3, and this is a 1 power here to the 1. Power of a power multiplies, so 3 to the 3y equals 3 to the 1. So like bases, I can set my exponents equal. 3y is 1. Divide by 3, so that's y. That's the reason that y is 1/3. But you know, you might have been able to figure that out without that process, but there is an alternative process to think of that. Okay, to the next ones. Log base 12 of 1. 12 to what power equals 1? Well, anything to the 0 power is 1, because let's say I had 12 squared over 12 squared. Rules of exponents say that's 12, 2 minus 2. Well, that's 12 to the 0, and what was 144 divided by 144? 1. So anything to the 0 power, that's a rule you should have memorized. Anything to the 0 power is 1. A billion trillion to the 0 power is 1. Next, 6 to what power is 216? Well, I know this is 3 because I know 6 cubed is 216. Here, 3 to what power is 81? And I know 81 is 3 to the 4th. Therefore, y is 4. Here, 4 to what power is negative 16? Okay, a couple things thinking about there. You might think, what about, let's just think about a couple things. What if it was 4 to the negative 2? Well, remember this negative makes it 1/4 squared, which would be 1/16, not negative 16. So that doesn't work. Maybe you want to think 4 to the 1/2. Well, that's just the square root of 4. Well, that's 2. So that doesn't work. The point is there any exponent that could turn a base into a negative? Is there any number of times you could multiply 4 by itself, positive 4 by itself, mind you, and it turn into a negative number? No. So this would be no solution. And here's the reasons. There is no exponent that can turn a positive base into a negative number. Now, I have another way to have you think about it. I want you to think of our exponential functions. Let's say that's 4 to the y. This has an asymptote at 0. This function is approaching 0, but never, ever going to reach it. So it's certainly not ever going to end up down here in the negatives and have a value of negative 16. So because our range is from 0 to infinity, it can never be a negative answer. It can never have a negative answer. So that's what else is happening there. All right, and our next one, 4 to what exponent is 1/4? Well, that would be a negative 1 because you would reciprocate that base. Okay, let's take a look at what's happening here on this one, log base 2 of 0. So 2 to what power can equal 0? For the exact same reason as before, because our function is approaching 0 and never ever going to reach it, that's our asymptote, because our range 0 is not included in our range, there is no exponent to include 0, to turn your base into 0. So this would be a no solution. Okay. All right. So this next section, these are some special logarithm rules. Okay, so these are some basic rules that you might have memorized, but I don't really typically memorize them. I just remember why, and then when they naturally come along, I know why. So the question is, you know, b to the, here's this log. Why is b to the log base b of 1 always equal to 0? And I would say the reason is because any base to the 0 power, by definition of exponents, is 1. Here it's saying log base b of b. Anytime that those values are the same, your answer is always going to be 1. Well, why is that? And the reason for that is because any base to the exponent of 1 is just itself. Well, what about this one? And this one, we had a sample of this. We had this earlier, and our answer was 5, 6. And so that's what they're saying here. Anytime these b's are the same here, your answer is going to be what that exponent was. And the reason is because b to the x is equaling b to the x. Okay, number 4. Why is this undefined if a is a negative number? And we just had that discussion. The reason is because, remember on your exponential functions, your range is from 0 to infinity. 0 is not included. And the same thing happens here. B to what power gives you a 0? Well, these are both no solution or undefined because, same thing, your range is from 0, not including 0. It doesn't ever equal 0. There's no exponent that could make that base equal 0. Okay, so that's the end of our part 1 to this. I'm going to do the graphing part in a separate